Alrighty, so I took a break and came back and spent like you want to say like 20 minutes on this, um, and I came up with a better solution. So what I was thinking was um, the things that I was stuck on before, like something where the word was, let's say TTAA-B, TTAA-C, where um, where you just can't determine, where basically you have to do a bunch of later comparisons to previous best. Like here originally TTAAB would be um, the start of the best thing, and if there's three friends that, or let's say the number of friends is three, so maybe start with TTA, something like that as your best thing, right? Lexicograph, lexico, lexicographically largest string. Um, and then if you see something later on where you say the first letter is the same and the second letter is the same, then you have to do a bunch of comparisons. The way that I was thinking about it is you'd have to do that every single time in terms of doing a full length comparison. But the index where you need to start that later comparison can change. So um, by doing some comparisons of like the second T to the second T here, the third A to the third A here, you can actually remove that those positions, possibly remove those positions from consideration later on, so that it's actually not like a n squared kind of deal. It's more like still like a one pass deal. Like you only pass that letter once, and the way that um, you can mostly do that. So um, basically, I keep track of a starting index of the best string. So really, you just need to worry about the starting index, and you don't track, like you don't actually create the substrings. And let's say you have another pointer towards the later strings that you're comparing to. So this is index is referring to some later string after the best after the best lexicographically largest string, starting at the best start. So in this loop, so first off, I'm going to keep a pointer to keep storage of the initial pointers. So I'll say previous is the best start index, current is the current index, and then I'm going to kind of go down the line. So um, I compare like this T to this T, and then the second T to the second T, and the third A to the third A, and the fourth A to the fourth A, until I see something that differs, right? Until I see something that's like B versus C, and then I know that when not this first one is actually lexicographically after this second one. So this is this while loop here. If the index, while the index is still in bounds and the letters are still the same, I can't make any sort of judgment as to which one is actually better. I'll increment both indices for the previous and the current kind of pointers. And then next is just a sanity check. If the index is at the end, then I'm not going to choose the later one because the earlier one will be better with it being longer. So I'll just break there. And then here's here's the tricky part. The if I reach a point where it's actually something that's like, let's say the word is T T T T Z, right? So what I do here is I compare this T to this second T because they're kind of very much similar. And like maybe the first T going all the way to Z, and this T would all go to this Z. And if it's something where a later letter that I'm doing comparison is actually better, strictly better than the first letter, then I'm just going to move my best start because that's going to be my new starting point. And that just makes sense, right? Like if you ever see a later letter that is better, strictly better than what you currently have, then you used to make that. But if you don't, then um, then you'll update your current best. Like here, if it's pretty much all matching, and you see something that is differentiating between the early string and the later string, then um, if the later string has something that's bigger, then you update where the start of that string is going to be your new best string, your new best index. So it's if the differentiating letter is not something that just strictly overrides the bestness, but it's like an improvement on a later character within that string, then I'm just going to use the improvement as my current the start of this current pointer, the start of the second word pointer as my best start. So it's almost like I'm keeping track of I want to say 4 things, kind of. My For my best start and my current, those are my indices of the previously highest lexicographically largest string, and the current is the start of the current set. And then I have index, which iterates through the current set, and previous, which iterates through the previous set. So like best start and current are pointers to the previous, to the like the max, and to the max and current substrings, while previous and index are pointers to comparison points within each of those strings up until when they're different, and based on difference either completely change your either based on difference, if improvement, change best start to current or to index. To index if the single letter is already better than the best starting letter, or to the current if the single letter at index differentiates the later substring as being slightly better than the previous substring after some number of iterations of the previous index. So anyways, that's the main gist of it. It's a tricky little thing. And then once you have that, you just, this is previous code. All this other stuff is like determining size of substring, given that each numFriends needs at least one character. So remain here is going to be how much you need to devote any back characters, any last characters at the end of the string for the numFriends. So if you have like 100 friends and the string starts at the best index starts at, let's say, 5, then that means that there's 5 friends that could be given 1 letter in the first 5 letters, and you need to have 94 other friends be able to get from the last letters after this best word. So the word is going to start at the best start index, and then it's going to stop at and remain away from the ending. Okay. Obviously, I'm kind of repeating myself some of the ending stuff that I did before in the last video, but summary, this can be what is the summary here? So keep track of best starting point. Use a loop to go through other starting point, other indices, pass after best, update, keep track of, or use a nested loop to iterate through secondary pointers to where the current and best substrings differ. If differ, if index of difference, if letter of difference, it makes for a strictly superior substring, update best to index, otherwise update. If letter of difference makes for slightly better substring, update best to start of current substring. And then so then there's no kind of double looping. You're generally going through each index exactly once. Yeah, you see here the index never goes backwards, and index always ends at n. So the time complexity here is going to be O of n, as index is going through loop up to n times, always increasing. Right, index, well, let's see, current, yeah, index is strictly increasing. So, and there is single letter comparisons. So those are constant. Whereas before it was string comparisons. For string comparisons, if you want to see which one's lexicographically longer, then it has to be the size of the string as the speed. Space complexity, this one is going to be much better. It's going to be O of 1, as you only track the index of best substring rather than the whole string itself. Like there's no splicing on this one, it's just tracking indices. Alright, that's a much better answer. Oh wait, did I actually show the answers? I mean, here's the runtime for it. Yeah, so it's like 7 milliseconds.